Hi all. In this session, we are going to discuss about a scenario-based question in Turing machine. So this question states, Rekha wants to convey a message to her friend. So he wants to two color flowers, a violet and orange, and he wants to group the n number of violet color flowers followed by n amount of orange color flowers. So you have to help Rekha to convey the message through the flowers. The first question is to design a Turing machine for the above scenario. So the scenario states the Rekha wants to convey the message through two color flowers, a violet color flowers followed by a orange color flowers. So it should be a equal number of violet color flowers and the equal number of orange color flowers. So n greater than or equal to 1. There should be at least one flower to convey the message. So this is the language which we can derive from the scenario is n number of violet flowers, which is equal to n number of orange flowers. So you have to first question is to construct a Turing machine for the above scenario. So I'm going to consider the violet color flowers as A and orange color flowers as B. So as we all know that Turing machine is it uses a memory called tape, and the tape contains infinite number of cells, and all the cells by default is filled with blanks. We're going to represent the blanks with B, and once you have the input will be filled in the tape from the left hand side. The language for this is A power n, B power n, and the string generated by the language is equal number of A's and equal number of B's. So this is going to be an infinite language. The logic I'm going to use to check the acceptance of the string is in the tape. So I'm going to use a string. I'll take this n is equal to 3. So you have infinite number of cells here. So I'm going to use the logic. The header will scan through the cells in the tape. When it finds A, the A will be replaced with X, and you are going to move the tape head towards right until you find B. Once you find the first B, for the one A, this B will be changed into Y. And the tape head will traverse back in the left side, and it will traverse to select the second A, and the second A will be matched with the second B. So this will be continuously checked until I find the total number of A's is equal to the total number of B's. So this is the logic I'm going to use to construct my Turing machine. The tape head will be initially in the first cell. So the construction is in the state Q now. When I encounter A will be replaced with X, and the pointer is going to move right. In the state Q naught, when I find A will be replaced with the X, and pointer is going to move right. The replacement variable is your choice. I have chosen X. You can choose any variable. So I'm replacing the variable to make the machine understand that A has been already encountered. I have to match one B with this A. So no matter how many number of A comes, I have to keep A as it is, and the pointer has to move right. because I have to match 1A with this 1B. So as soon as I encounter B, right, when I encounter A, the pointer will be moved right. So as soon as I encounter B, B will be replaced with some other variable. I'm using the variable Y. So for this 1x, 1y is replaced. So the pointer has to move until I find the first B. When I find the first B for the matching A, I have to replace this B with Y, and then I have to move left. So for this 1A, 1B is matched. So after matching this first B, pointer has to move left to pick the second A. So this has to be traverse in the left side. So no matter when I travel left side, I may encounter any number of A's. Just keep A as it is and move left. You may encounter some Y also, because when you are cancelling the second B, you may traverse through the left side. You may encounter Y also. So when you encounter Y, then replace it Y and move left. So left. You have to traverse to pick the second A or the next A. So when can I know that this is going to be the next A? So when you encounter X in the leftmost side, then you can know that the second cell is the next cell you have to process. So this has to continue until I find X. So when I find X, I know that that is the last processed A. So after that, once I hit this X, I have to move back to the next A. And this loop will continue for all the number of A's and B's. So the next A will be chosen. The next A will be converted into X. The pointer will move to the right hand side. When you move to the right hand side to pick the next match for the second A, you may encounter Y also, because the already processed B's would have replaced with Y. So you have to continue with that Y. Don't change anything. Just continue with that Y. Replace Y with Y and move right. So this process has to continuously done for all the number of A's and B's. Now, what is the stopping criteria? So this A, first for the first A, the first B will be cancelled. Second A, second B will be cancelled. The third A, third B will be cancelled. So in the state Q naught, when your pointer again comes to Q naught, in Q naught, if you find Y, it means that all the X's, A's are processed and it has been converted into X. So this is the stopping, halting criteria for the Turing machine. So you have to, no matter how many number of Y comes in Q naught, accept as it is. And when you reach blank, so the you will find in Q naught, you will find Y. So move. So one at a time. At a time, you can encounter a blank. So that is the acceptance state. So this is the Turing machine which has been constructed for the language A power n, B power n. The second question, you have been asked to design a Turing machine transitions the transition function for every state should be clearly mentioned through the transition function. For the state Q0, the first transition is in state Q0, if you encounter A, then you have to replace that with X and you are going to move right. You have to mention in the transition function state-wise. In state Q0, if you encounter A, then you are going to move to state Q1 and you're going to replace it with X and the pointer has to move right. So the transition function should be written in such a way that the LHS contain the current state and a current input you are encountering, and the RHS has a triplet values. The state which you are moving when you encounter the input A, and the replacement for the input symbol if it is required, and the direction of the pointer. So this is a triplets, the next state, replacement, and then direction of the pointer. So the second transition, in Q0, there is only one transition with respect to A. And in Q1, we have two transition with respect to Y. It is going to stay in the same state and there is no replacement. Y will be replaced with Y and pointer is moving right. The third transition in Q1 is Q1. When it encounters A, Q1 will be, the state will be Q1 only. A is going to be replaced with A. There is no replacement and pointer is going to move right. The fourth transition is in the state Q1, if it encounters B, then it will move to the state Q2 and the replacement is going to be Y and the pointer is going to move left. And the fifth transition with respect to Q2, when you encounter A, you're going to stay in the same state and replace A with A and the pointer is going to move left. In the state Q2, when you encounter Y, you're going to stay in the same state. The replacement is Y and the pointer is going to move left. And in the state Q2, when you encounter X, you're going to move to the initial state Q0 with the replacement value as X as it is, and now you're going to move right. And next one is in the state Q0, if you encounter Y, then you have to traverse to the state Q3 with the replacement of Y as Y and pointer has to move right. So in the state Q3, no matter how many number of Y comes, I'm going to replace and stay in Q3. The pointer has to move right. And the last transition is in Q3, when you encounter blank, then you will move to the acceptance state and replace the value with blank and you can move left or right. So totally, there are 10 transitions. This is how you are going to write the transition. If you have been asked to write the transition of the given Turing machine, you have to construct the Turing machine and you have to write all the possible transitions respectively to all the states. So as per my example, I have 10 total transitions. So the transition contains triplet value in the right hand side, the state in which we are moving after encountering this input, The value that has been replacing instead of this input, if it is required, the replacement will be done. Otherwise, the same value will be replaced here. And the third value is the movement of your pointer, whether you are going to move right or left. So this is how you are going to write the transition. Another question in the same part is, you have to draw the transition table for the given Turing machine. So transition function done. Next, I'm going to show you how to draw the transition. So now we have done with writing the transition. The next step is to draw the transition table. The transition table can be drawn with a list of transition which we have wrote from the given Turing machine. So we have totally 10 Turing machine. The transition table holds all the state in the row Q0, Q1, Q2, Q3, and Q except, and the column contains the possible tape symbols A, B, X, Y, and the blank symbol. So every transition has to be written in a right place. Q0 with respect to A, you have to see whether any transition in the given list of transition. Yes, Q0 with respect to A, we have a transition. It has to move to the state Q1 and replacement with X and move right. The transition has to be copied here. And same as like Q0 with respect to A. Next, we have to check with Q0 with respect to B. There is no transition for Q0 with respect to B in the given list of transition. So you have to give a dash here. Dash means there is no transition exist for the respective input symbol from the given Turing machine. Next, Q0 with respect to X. Q0 with respect to X also no transition to, so dash. Q0 with respect to Y. Q0 with respect to Y, we have a transition. We have to keep Q0, Q3 as it is in the same state. And sorry, in Q0, when you encounter Y, you are going to move to the state Q3 and replace the value with Y and move right. So likewise, all the 10 transition will take the correct place in the transition table. So Q1 with respect to A, you have to find is there any transition? This has to be replaced here. In this way, you have to fill all the values in the table. So state versus the possible tape symbols. So this is transition table for the given Turing machine. And the next question is, they asked you to write the instantious disk. The next question for the Turing machine is to write the instantious description for the input AABB. The instantious description for a Turing machine will capture what is going out at any moment. So it basically contains all the information of the current state of your computation. So whatever is your current state, it will help you to read out every state carefully for scanning the given input symbol. The given instantious description in the question is, you have to write the ID for the input AABB. The instantious description has to start from the initial state Q0 and it will consume all the input. Every state of transition will be scanned through every input, and then based upon your transition, if the input takes you to the final acceptance state, then the ID will justify that the given input will be accepted by your machine. This is the symbol for the instantious description. Simply, we can call this as an ID. So we'll start from the state Q0. In state Q0, if your machine says A, so in state Q0, if your machine says A, the machine will replace the A with X and it will move one step right. So this A will be replaced with X and machine will move one step right and it will be changed to the state Q1. One step it will be moved, changed to the state Q1 and the remaining input will be pasted as it is. So now we are in the state Q1. In state Q1, if it says B, so in state sorry, in state Q1, if it says A, so the machines replace A with A and it will move right. A will be replaced with A and machine will stay in the same state. One step it moved right. Now, in state Q1, if it says B, so in state Q1, if it says B, the machine is converting, the replacing B with Y and it's going to be move left. So I'm going to move one step left as well as it will be moving to the step Q2. So I'm moving one step left. So one step left means Q2 will come here because I moved to the state Q2 and this remaining inputs will be copied as it is. B will be converted into Y and this B will remain as it is. Q1 moved one step left and this A will come this. Now, in state Q2, if it sees A, then in state Q2, if it sees A, then it will stay in the same state, but it will move left, right? So in state Q2, if it sees A, it will move one step left. So it's moving one step left and keep A as it is and the remaining input also copied as it is. Now it is in state Q2. In state Q2, it is seeing the input X. So it is replacing the X with X, but it is moving right one step ahead and also changing the state to Q0. So in state Q2, if it's saying X, it's going to move one step right, and it's going to be have a state change Q0 and the remaining input as it is. In state Q0, when it sees A, then again the same process, A will be replaced with X and this will be moved one step right and state will be changed to Q1. A will be moved to X, one step forward, right side, state will be changed to right, the remaining input Y and B. In state Q1, if it says Y, again in Q1, Y stays in the same state but move right. So I'm going to move right. I'm going to move right, saying in the same state. In state Q1, if the machine sees B, in state Q1, if the machine sees B, transform, replace it to Y and move left. So I'm going to move left. One step, I'm going to move left and I'm going to transform this B into Y. I think here. So in Q1, with respect to B, it's going to move to left and 2. So X, I'm going to move to one step left, that is Q2, the state change. This B will be changed to Y. Now again, this Q2 will see Y. In state Q2, if you see Y, what will happen? So see the transition. Q2 with respect to Y, stay in the same state, replace Y with Y and move left. Now I'm going to move left. X, Q2, X, Y, Y. Now in the state Q2, again I'm seeing X now. In the state Q2, if I see X, I have to move right. I have to move right and I'll change to state Q0, followed by Y, Y. And after the input, all the tape cells will contain blank. So after your input, all the tape cell will contain blank only. That you know very well. And the next step, in state Q0, when you see Y, now you started seeing Q0 Y. So when you see your machine in state Q0, when you see Y, you have to replace it with Y and move right. So I'm going to replace that with Y and I'm going to move right. Move right, but the change of the state has to be made. So now the state change is Q3 and then Y and then followed by infinite number of blank symbols. In state Q3, when I see Y, again, no matter how many number of Y comes, the state Q3, when Y comes, replace it with Y and move right. So I'm going to move Q3 with Y and I'm going to see the next cell. In state Q3, when I see blank, so the transition says in state Q3, when you see blank, then the state will be Q accept. So no matter how many number of blank comes, it will get accepted. So this is the ID for the given input XX, given input AA, BB. So this is how you are going to write the instantious description for the given input. Instantious description has to be written in such a way that the current computation of your machine will be given step by step. The last question for the scenario-based question is encode the given machine. So you're going to encode your Turing machine. So basically, encoding the Turing machine is converting your given Turing machine in the format of bit strings. The encoding of a Turing machine is usually denoted as a tag M, and this string is going to be encompass all the information of the 7 tuple that describes M. You know the tuple notation for the Turing machine. We are going to encode the Turing machine that converts the 7 tuple as a binary string. So I'm going to convert the 7 tuple as a binary string. Binary string. So this is a just simplification. The encoding of this M is just a string that describes how the Turing machine works. So a Turing machine can be considered as an universal Turing machine if it is capable of simulating the other Turing machine. So it is represented as M, W. So first of all, we will see how to encode the given Turing machine. So this question, they were asked you to encode the Turing machine of A power n and B power n. So before encoding the Turing machine, you have to assume the encoding of your machine with respect to the states, with respect to the input alphabets, and with respect to the possible tape alphabet, and then left side move and right side move. So first of all, I'm going to assume a encoding values for the state. So here for my machine, there are state Q1, Q0, Q1, Q2, Q3, and Q accept. So for all the states, I'm going to assign the encoding string value as 0 and 1 0 greater and 3 zeros for Q2 and 4 zeros encoding for Q3. And for acceptance state, I have 5 zeros. The first step to be done is assume the value for all the state. You all know in tuple notation, the first parameter is total number of states. So the first parameter, total number of states, encoding values has been done here. If you have one more state Q4, then assign 5 zeros for the Q4 and the last acceptance state 6 zeros. So 1 0 can be incremented everywhere. So I have assigned the encoding values of zeros for all my states. And then the input alphabet. So input alphabet A will be assigned with single zero and input alphabet B will be assigned with 2 zeros. So I have assigned the encoding values for the input alphabet as well. And third one, tape alphabet. Tape alphabet is A, B. Already I have assigned for it. In addition to that, X. So 3 alphabets, input bit string 3 zeros, and Y I'm going to assign it as 4 zeros. So all the possible tape input, I have assigned the bit string value. And the one which is left is moving direction. So either your pointer is going to move left. So I will assign the bit string as 0 and move right bit string as 0, 0. You can also assign right as 0 and left as 0, 0. So the assumption of your encoder string should be given properly. In some videos which you have referred, you may also find that they may assign 1 as their encoded bit string value. You can use either 1 or zeros if you wish. I have assumed all the zeros as my encoded string value for my Turing machine. Now I have assigned the encoded value for all my Turing machine. Now, since the question is to encode the entire machine, you have to replace this encoding value for all the transition given for your machine. So you have to start from the first transition until 10th transition, you have to encode this value. So I'm going to encode it for starting from transition 1. Just go with parameters and replace the respective binary string. The first parameter is Q0. Q0, the value is 0. So I have replaced with 0. And for A, just see what is your encoded string value. A also, the value is 0. To know the separation between these two parameters, these two parameters will be separated with 1. When you have a separation, when you want to instruct a machine, this is the first encoded string for the state. Now, before the next encoded string, you should use a separator. I'm using 1 as a separator. And for A, I'm replacing with the encoded string 0. So LHS done, and I'm going to move to RHS value. So before I'm moving to start the parameters of RHS, I'm going to give the separator value. The separator value done, and next one is Q1. Just see for Q1 how many number of encoded string will come. The encoded string value is 0, 0. I'm replacing with 0, 0. The next parameter is capital X. Capital X you have to replace with 3 zeros. So before proceeding with the encoding string value of capital X, give the separator value and then go with the encoded string values. Capital X, done. And then again, I have to move to the right side as per this transition. So before moving into right side, give the separator 1. And for right, I have assigned 2 zeros as my bit string. So 2 zeros. Now I have encoded the entire first transition. This is the first encoded string value for my first transition. I'll repeat it once again. when you write the encoded value for each transition, you have to take a parameter by parameter, see the first parameter, and just replace it with the encoded string value. When you move to the next parameter, before moving to the next parameter, just give one as a separator. Now everything done for the first transition, you have to move for the second transition. Encoding the machine means all the transitions should be encoded. Now I'm going to move for the second transition. The separator that has been used to separate the transitions are double one. So to separate two transitions, I'm going to use double one as my separator. And to separate the parameter inside each transition, I'm going to use separator one, single one as a separator. Now I'm going to the second transition. First parameter is Q1. Just search for the Q1. Q1 has two encoded string as 0, 0. And then capital 1. So I'm moving to the second parameter. So I have to use a separator 1. For Y, just see Y, how many number of encoded zeros? 4 zeros. And I'm going to letters, next parameter. I'm going to use my separator 1. And then Q1. Q1 is 0, 0. And the next parameter I'm going to move. Parameter is Y. Encoded string is 4 zeros. That has to be separated with single one. And then 4 zeros. And then I'm going to move right. For move right, I assumed 2 zeros as my encoded string. I have to use the separator 1 before writing the encoded string value of the parameter R. Encoded parameter value is 0, 0. Now I have written the encoded string value for the transition number 2. Now I'm coming for the transition number 3. Before start writing the encoded string value for the parameters of the third transition, I have to separate that with double one. So I have used the double one as my separator. I'll start with the transition number 3. Transition number 3 starts with the parameter Q1. Q1's encoded string value is 0, 0. And then separator 1. If it is within the transition, for each parameter has to be separated with single one. And then A, for A, I have used a single 0 as the encoded string value. So single 0 followed by the separator. And then Q1, Q1, double 0. And then a separator 1. And then A, the value is single 0. And then a separator 1. And then right is double 0. Transition 3 done. So before going into encoding of transition 4, transition number 4, how to give double 1 as a separator. So this is transition number 1. This is transition number 2. And this is transition number 3. And so on. I am giving and so on here, but you have to encode till 10th transition. You are allowed to write continuously the encoded string, but you have to complete all the 10 transitions. So this is the encoded. When you complete the 10th transition, that is the encoded value for the given Turing machine. So this is how you are going to write the encoded value for the given Turing machine. You should not forget to write the assumption of your bit string for all the states and then possible input symbol, take symbol, and also for left and right direction move. Thanks for watching, guys.